conditions, and we are actually seeing of a 1D condition. Okay, so we are actually thinking of some 1D condition, um, which is unsteady with heat generation. Okay, so yeah, so initially we were actually seeing one steady without heat generation. So our equation actually reduces to the simplest possible. D square T by dx square is equal to 0. Okay. Then we started to solve the equation using some boundary conditions and all. So we were actually saying the heat flux is always perpendicular to the isotherms. Okay, so therefore the as we are actually saying, the heat flux is actually a vector quantity. Therefore, we actually said it's actually the values can be actually written in any of the it can be actually represented by vectors like I, J, and K in terms of unit vectors in each direction. Okay, so now we are actually saying it is actually having this direction also, and the direction is always perpendicular to that as actually the isotherm. And then using the boundary conditions, we actually solve the equation, and we actually saw that for the constant temperature boundary condition on both the sides. Yeah, so this is actually the conditions we are actually seeing. So temperature, constant temperature condition on both the sides. We actually saw that. Uh, yeah. So we actually saw that the temperature variation, it is actually a linear temperature profile. So in that case, the heat flux is actually not a function of x, okay, not a function of position within this slab. And we actually see so what is actually the total heat flux and all. So since the temperature variation is actually linear, we can actually write dt by dx as t1 minus t2 by L itself. Okay. And then we actually said that this is actually similar to or it can be actually analogous to the electrical system. So in which we are actually writing I is equal to V by R, where voltage as well as the resistance, electric resistance. This is actually similar to what we can actually write for the 1D heat conduction without heat generation also. So in that case, we are actually writing T1 minus T2 divided by L by Ka. In the electric analogy, we are writing E1 minus E2, which is actually the potential difference divided by L by sigma, where sigma is actually the electric conductivity. So we can actually see that L by Ka, it is actually analogous to the electric resistance. So we are actually calling it as thermal resistance. Okay, so we said, yeah, thermal resistance for conduction is therefore L by Ka, which is equal to T1 minus T2 divided by the Q conduction. So same way we can actually write for convection as well as radiation. So for convection it is 1 by HA, and radiation is actually going to be 1 by HRA, where HR, which is actually a we can actually say an effective heat transfer coefficient for radiation, we can actually derive, and we actually saw what is actually the value for that also. So that is actually okay for us. We are actually just happy with that. But we are having some doubt on what if a two kind of resistance comes in a series and all. Okay. So anyway, before that uh, we were actually trying to find the temperature profile within a slab with another boundary condition, in which we are having a boundary condition of constant temperature at one side, and we are having a boundary condition of convective heat transfer at the other side. So in that case also, we are actually trying to reduce the temperature profile, and we actually got the temperature profile like this: T1 minus H into T1 minus T infinity divided by KHL into X. So everything is actually unknown. T1 we actually know because that is actually one condition. H and T infinity, that also we actually know because that is actually another boundary condition. K is actually the temperature property, heat transfer coefficient of the thermal conductivity of the slab we are actually talking about. Okay? So that's why we actually stopped in the last class. So any doubts still here?
No, sir.
No, sir.
Yeah,
No, sir.
yeah. So now we are actually going to see a little bit deep onto this particular equation, which is actually named as D. So we can actually write it in yeah. So this one, this is actually the temperature profile with it, right? So we have to actually find what is actually the Q passing over that. Okay. So we have to actually find Q. Q is equal to minus Ka dt by dx. Okay. So but what is actually dt? Uh, dt by dx is equal to. Can anyone say what is dt by dx? It is equal to.
C1.
C1 is actually fine, but what is actually C1 in this context? So h into T1 minus T infinity divided by K plus HL, right? So T1 there is no X quantity there, so that is actually going to be cancelled that. Okay. So now Q is equal to minus, so minus of minus we can actually cancel it off. So minus or minus Ka into minus H into T1 minus T infinity divided by K plus HL. So is equal to KAH uh, T1 minus T infinity divided by K plus HL. Okay. So that's where that's what heat flux. Okay. So total heat transferred to the system. Okay. So total heat transferred to the system. Now we are actually going to rearrange this one. Okay. So now we are actually going to rearrange this one. So what we are actually going to do is we are actually going to take this KH and dividing it with the denominator terms. Okay. So if you are actually doing that, what you are actually going to get is Q is equal to T1 minus T infinity divided by K divided by K into H into A plus H into L divided by K into H into A. Okay. So if you are actually cancelling the like terms, okay, like quantities, then we are actually getting Q is equal to T1 minus T infinity divided by 1 by HA plus L by KA. Okay. But what is actually 1 by HA? What is actually 1 by HA? HA is actually the,
Convecting resistance.
yeah, very good. So here we can actually write divided by, okay. So R convective plus R conductive. Okay. So in other sense, if we have to actually write in the order, okay, write in the order, we can actually say R conductive plus R convective. Okay. And what is actually the temperature we are actually now talking over here? Our condition is actually such that it was actually, this is actually our slab. We are having T1 at one surface, we are having H and T infinity at the other surface. Okay. So now we are actually saying is that the total heat flux is equal to total potential. What is actually the total temperature potential over here? The total temperature potential is actually the difference between the maximum temperature difference. It is actually T1 minus T infinity. So we actually assumed the Q is actually passing in this direction. We assumed T1 is actually greater than that of T infinity. Okay. So therefore, the potential is T1 minus T infinity, and we are actually saying Q is equal to T1 minus T infinity divided by R conduction plus R variation. Because when it is actually passing through the slab, there is actually conductive resistance, and after that, from the slab to the boundary condition or to the fluid outside, there is actually convective resistance. Okay, so here you can actually write T1 minus T infinity divided by R conduction plus R convection. So that means here you can actually write uh, two modes. Two modes. What are the two modes? Conduction and convection. Okay, two modes of heat transfer. Heat transfer. Okay, so how we can actually write it? It is actually acting like a resistance in series. Okay, so two modes of heat transfer acts like resistance in series. Resistance in series. Okay, so therefore that's what the main catch of this. So from the basic derivation itself, we have actually seen that if we are having a resistance in series, we have to simply add up, or we are having this various boundary conditions or various mode of heat transfer in series, then we can actually write it as uh, series resistance, and we can actually derive it. Okay, so in order to derive this particular equation, we actually first find what is actually the temperature variation inside, and then we actually took the dt by dx, and then we actually did the answer. Okay, so but if you are actually want to use this resistance analogy, okay, if you want to use this resistance analogy, we can actually do this uh, very easily, right? So here we are actually saying we are having a T1 over here, okay, and after that we are having this conduction, okay, conduction resistance, which is L by Ka. At the end, you are having this temperature T2, okay, we are having the temperature T2, which is actually again unknown, okay, and then we are having the convective resistance, and after that you are having the H1 by HA. Okay. 1 by HA we are having. And after that you are having this. So using this electric analogy, you can actually directly write potential. Okay, so that is T1 minus T infinity divided by L by Ka plus 1 by HA. Okay, so directly you can actually find what is actually the heat flux. Okay, so that is actually the beauty for this resistance analogy. So basically, if from this condition, you will not get the temperature profile with it. So in order to find the temperature profile, again, you have to actually go with the basic conditions. Okay, but in many of the conditions, we are actually more interested in heat flux in many of the cases. So for that particular condition, this is actually very easy. Okay. So that is actually one way of doing this. Okay, we can actually call it as call this equation as f. Okay. So that is actually so yeah. From the basic derivation itself, we actually wrote that if the resistance comes in or different modes comes in series for 1D without heat generation, you have to simply add up the resistance. Okay, so that's what we actually rated for equation E. Okay, so but equation E can be also derived in some other way. Okay, so can be also derived as below. Derived as below. So here what we are actually saying is the condition is that Q conduction in wall. Okay, so Q conduction in wall, since there is actually no heat generation, nothing is actually there. Whatever heat is actually conducted in the wall till the surface should be equal to the heat convected to the uh, fluid outside or the liquid outside. Okay, so therefore we can actually write as Q conducted in the wall is equal to Q convected out. Okay, so Q conduction in the wall is equal to Q conduction out. So that's what we are actually going to write. So what is actually the Q conducted in the wall? We can actually write, since there is no heat generation of nothing is actually there, we can actually write Ka T1 minus T2 divided by L. Right. So this is what we actually derived in the previous boundary condition. And Q convected is HA into T2 minus T infinity. Okay. So that's what we actually wrote. And then we can actually write as T1 minus T2 is equal to L by Ka in terms of thermal resistance. We can actually write T2 minus T infinity divided by 1 by HA. Okay. Yeah. So this is what we are actually writing. So now we are actually going to use a particular theorem which is actually known as dividendo componendo rule. Okay. So by using dividendo componendo rule, okay, what it actually says is if it is a by b is equal to c by d, then we can actually write as which is it is actually going to be equal to,
A plus B by A minus B equal to C by C plus D by C minus D.
yeah, there are actually many ways in which we can actually write. We can actually write as a plus c divided by b plus d. Okay, so this is actually one way of writing it. Yeah. So whatever you said is also true. There are actually many ways in which we can actually write. This is actually one identity from dividend or common under. Okay. Yeah. So this is actually simplified idea. I will actually say. So whatever you said is actually the general one. This is actually simplified idea. Okay. So if you are actually going to do that, what you are actually coming up is T1 minus T infinity divided by, because T2 will be actually cancelled. One minus T2 is there, plus T2 is actually there. Okay, so those will be actually cancelled. Then we can actually write T1 minus T infinity divided by Lk plus 1 by Ha. Okay, so this is what we can actually write. So this is again equal to T1 minus T2 divided by L by Ka, or we can actually write Q. Q is equal to T2 minus T infinity divided by 1 by Ha and all those things. Okay. So yeah, so this is actually the general form for this thermal resistance. Okay, or we can actually write as total potential difference, or we can actually say total temperature potential difference divided by total thermal resistance. Okay. So in this particular case, total temperature potential is actually T1 minus T infinity, and the total resistance is convective resistance plus conduction resistance plus convective resistance is equal to partial temperature potential difference divided by thermal resistance over that region. Okay, thermal resistance thermal resistance over corresponding length. Okay, so what does that mean? So a partial potential difference is T1 minus T2. So it is just a part of the wall system. Our wall system is from T1 to T infinity. A part is actually from T1 by T2 or from T2 to T infinity. These are actually two different parts. Okay. It is equal to partial temperature potential difference T1 minus T2 divided by temperature resistance over the corresponding line, which is equal to L by K, or T2 minus T infinity divided by 1 by H. Okay. So that is actually the how we can actually use this thermal resistance for different conditions. Okay. Yeah. Sorry, I should have actually written it in lecture 7. Anyway, yeah. So any doubts in that? Yeah.
No, sir.
Yeah. So now we are actually going to see a little bit advanced version for this. So in which case, what we are actually going to say is we are actually going to have a particular slab. Again, we are actually going to have a slab, a big slab we are actually going to have. Okay, in this case we are actually going to have a big slab, but in this big slab you can actually see that there are actually three different type of materials. Okay, so three different type of materials are actually going to be there. Okay, so this type of materials having different conductivity. Okay, so in this case we can actually say Ka. Okay, and this is actually material A, and this is material B, and this is actually material C. So it is having conductivity Ka, and it is having a length of say La, and the B material it is having conductivity Kb, and it is having a length of say Lb, and C material it is having conductivity Kc, and it is having a length Lc. Okay, so here we are having different type of materials to make a single slab. So such type of walls or a slab or wall, it is actually known as composite wall. Composite wall. Okay, it is actually known as the composite wall. So we can actually write materials of different thermal conductivity and thickness. Materials of different thermal conductivity and thickness thickness are combined to make a wall. Are combined to make a wall. Make a wall. So such a wall is actually known as the uh, composite wall. Okay. So here we are actually writing say temperature. Here we are having a boundary condition say H1, and it is having a temperature of T infinity 1. Okay. And at the surface we are having temperature T1 and temperature T2 and temperature T3 and temperature T4, and here we are having H2 and T infinity 2. Okay. Obviously, we can actually use our basic equation is d square t by dx square is equal to 0, and based on that, obviously, we can actually use various boundary conditions, and it is actually possible to derive the basic equation of temperature profile, etc. Okay? But it is actually a bit cumbersome for us. So what we can actually go for is obviously we can actually go for the uh, thermal resistance analogy. Can anyone say how many thermal resistance are actually there? How many components of thermal resistance should be actually here now?
Five, sir.
Yeah, very good. So which are all the fives? We
So
can
three
actually write.
conductive and two convective.
Yeah, very good. So T infinity 1. Okay. So T infinity 1. T infinity 1 we are actually over here. This is actually the main temperature we are having. So in the convective at the surface, at this surface we are having one resistance, which is actually the convective resistance L1 by HA. So we are actually assuming the cross section area is actually same for all. Okay, so then only we can actually do the calculation. The cross section area we are actually assuming same for all. Okay, so one convective resistance is actually going to be there. Then we are having our first temperature, and through the conduction to the first material we are having LA by KA into cross sectional area, right? And we are actually going to reach T2. Okay, and when it is actually passing through the second material, we are having next conductive resistance. We can actually write LB by KB into cross sectional area, and we are actually going to reach the temperature T3. And when it is actually passing through the third material, we are having our third conductive resistance LC by KC, or here KB. Okay, KC into A. Okay, and then we are actually going to have the fourth temperature, and at the surface we are actually going to have the convective resistance 1 by H2 into A, and then we are having the uh, temperature of the fluid in the other side, which is T infinity 2. Okay, so therefore we can actually write what is actually the heat flux through this. Heat flux can be actually written as T infinity 1 minus T infinity 2, assuming, okay, so assume T infinity 1 is actually greater than T infinity 2. Okay, so Q is equal to T1 minus T infinity 1 minus T infinity 2. That is actually the full potential difference. And since we are actually considering the total potential, then we have to consider all the thermal resistance. Okay, so 1 by H1A plus LA by KA into A plus LB by KB into A plus LC by KC into A plus 1 by H2A. Okay, so we can actually write this as 17, equation 17. Okay, so we are actually following the same numbering throughout. Okay, uh, somewhere we are having, yeah, okay, 1 minute, which is actually 15 and 16. I'm just checking the 15 and 16 numbers. Yeah. Here the thermal resistance for convection is actually numbered 15. Thermal resistance for radiation number 16. Yeah. Now this is actually number 17. We can actually write. Yeah. Okay. So this is actually how we are actually finding this one. Okay. Anyway, we can actually write as Q. This is again equal to a partial difference also, right? So we can actually write as I don't know, T infinity 1 minus T1 divided by 1 by H1A, because since there is no heat generation of something, So whatever the heat flux in this direction, it should be actually go out from this surface also. Okay. So since there is no heat generation, the Q flux is actually constant throughout. So whether we are actually finding the total potential or partial potential doesn't matter. The heat flux is actually going to be same throughout. Or you can actually write a T1 minus T2 divided by LA by KA into A. I don't know, maybe you can actually write as T3 minus T4. Okay, so divided by T3 minus T4 means this section. So LC by KC into A, and so on and so on. Okay, yeah. So that we can actually write. So we can what we actually said previously was the partial potential divided by the thermal resistance over that particular range. Okay, so we can also write T1 minus, I don't know. So T1 minus say T3. Okay, so T1 minus T3, if you are actually considering, then what all resistance will actually come over here? Okay, so this is actually T1, this is actually T3. We are actually saying T1 minus T3. Then what are the resistance comes in its way? Then we have to write LA by KA into A plus LB by KB into A. That's it. Okay. So this is again equal to whatever we actually shown earlier. Okay. So in this way, you can actually calculate the temperature at different surfaces also. So this T infinity 1 and T infinity 2 we actually know, and all the other quantities we actually know, right? So from this you can actually calculate what is actually the heat flux. Then from this particular equation you can actually calculate what is actually T2. Then this equation you can calculate T2. So from this you can actually, yeah, so one more equation will actually come in between, which is T2 minus T3 divided by its thermal resistance. From there you can actually calculate T3. So again from this you can actually calculate 3 4. So likewise you can actually use various equations or various methods and or various potential, and you can actually calculate the temperatures at different sections also. Okay, yeah. So that is actually the yeah. So that's how we can actually make use of this thermal resistance for our calculations. Okay, yeah. So here you are actually writing uh, Q. Okay, so we are actually writing Q is equal to delta T divided by R total. Okay, so that's what we are actually writing, right? So, but always it is actually often convenient to work with an overall heat transfer coefficient. Okay? So this is actually something. It is actually analogous to electric anodes. It's not something that we can actually talk of, say, heat transfer point of view. Okay? So what we are actually writing is, it is often convenient to work with, and so work with an overall heat transfer coefficient. Overall heat transfer coefficient. Okay? Heat transfer coefficient. Okay. So what we are actually trying to analyze is that, so we are actually considering all these into another form of a overall heat transfer coefficient. Okay. So we are actually going to write it like Q is equal to uh, delta T by R total. We are actually writing, right, R total. We are actually assuming it is equal to UA into delta T. Okay, so where this U is the overall heat transfer coefficient. Okay, U is actually the overall heat transfer coefficient. Okay, so therefore we can actually write as U is equal to 1 by R total into A. Okay, so R total inside itself, it is actually going to be there. So this U is equal to R total into A. Okay, how we can actually write is, we can actually write for the particular example what we actually saw 1 by h1, because into a we are actually talking about, so we have to take out all the a's here. So 1 by h1 plus la by ka plus lb by kb plus lc by kc plus 1 by h2. Okay, so that is actually the overall heat transfer coefficient for this particular example. Okay, so we can actually write it as 80. So this particular equation, we can actually write it as 80. Okay, so that's how we are actually writing. So what you have to do is you have to actually calculate the overall heat transfer coefficient, and then you can actually find from the heat flux directly. You can actually find just for convenience we are talking about. There is no other particular physical significance. Nothing is actually there. Just for convenience, we are actually talking about this. Okay, so therefore we don't have to talk about the R total or R total all the time or something. You can actually talk about the overall heat transfer coefficient. That's it. That is more from a what we can actually say a thermal point of view. That's it. But just for convenience, we are actually saying this. Okay, yeah, because this is again going to be more convenient when we are actually dealing with this heat exchangers and all those things. Okay, so based on that, we are actually using this term overall heat transfer coefficient. So when you are actually talking about the heat exchangers, again, we can actually use this kind of a thermal resistance analogy. But in those cases, the more appropriate term is actually the overall heat transfer coefficient. Okay, so based on that, we are actually saying we are actually using the term overall heat transfer coefficient. Okay, yeah. So now we are actually going to have a little bit more complex system. Yeah. So here we are actually talking about our slab, right? So we are having our slab like this, a big slab we are having like this. So initially we actually partitioned it three. Okay, that was actually easy for us, and we actually assumed the heat flux to be 1D, 1D and all. So if you are actually assuming 1D, again, you have to actually think that at any particular section, if you actually take, okay, so if you are actually take any particular location you actually take, the temperature should be actually, say, this is actually at a distance x1. Okay, so the temperature will be actually constant at that particular location, right? So here, if it is at a location x2, the temperature will be x2. Okay, so perpendicular to the x direction, the temperature is actually going to be constant because we are actually saying heat flux is in x direction only, and we know that heat flux is always perpendicular to or normal to that of the isotherm. Isotherm is actually the imaginary line which is actually connecting the locations of constant temperature. Okay, so therefore, the isotherms will be actually perpendicular to that of that of the x direction in these cases. Okay, yeah. So that's what we were actually saying in that. So now we are actually going to have a bit more complex one. Okay, so here what we are actually going to do is, suppose if you are having a material like this, we are having four different materials now. Say A, B, C, and D. So we are having temperature T1, temperature T2, say T2 dash, T3, T3 dash, and T4. Okay, don't write this now. Okay, don't write this now. I'm just giving something. Okay, so we are actually saying this is actually LA. The distance is actually LA, and this distance is actually going to be LB is equal to LC, and this distance is actually going to be LD. Okay, so whatever I actually wrote is actually true, or is there any corrections we need to actually do? Whatever I wrote, the temperatures are actually true.
No, sir.
Why?
Let it be see
Keep
that
it
T2
same.
should be same and T3 to be same.
Yeah, very good. Because here you have to write T2 only. If there is actually going to be T3 dash, then what happens is that the heat flux will be in some other location direction. Okay. So therefore, so even though the practically what happens is that this is actually going to be a 2D conduction, obviously. Okay. So practically in many of the practical conditions, it is actually going to be 2D, but we are actually assuming it to be a 1D conduction. If it is a 1D conduction, that means the full surface should be of same temperature. Okay, So full surface of same temperature. So if you are actually taking any location in between, okay. So if you are actually taking any location in between, the temperature should be actually same throughout. Okay. If it is actually location x1, so it should be of same temperature throughout. Okay. So therefore, we can actually see that T2 is actually constant, whether it is for the material B or C. T3 is also constant, whether it is for material B or C. Okay. Then what is actually changing through that? Okay. If a temperature is actually same, then what is actually, or how does this actually matters if we are actually talking about? Okay. So that's, yeah. So that's what we are actually going to see. So we can actually write this as a temperature profile or a thermal resistance. We can actually write, then it is actually going to be more easy for us. So we actually neglecting this H1, D infinity 1, etc. We are actually neglecting. So now we are actually comfortable with that. Just for this condition, we are actually saying. Okay. So first we are having our T1, and after that everything is actually fine. LA by KA into A. Okay. So that is actually fine for us. Again, we are just assuming that the height uh, practically, but yeah. So we are actually assuming the height, say, uh, okay, so if this is actually the full height, if this is actually full height h, we are actually assuming h by 2 and h by 2. Okay, h by 2. So that means B and C are actually equally divided. So how we can actually write over here? So after this, when it actually comes over here, obviously we are having our temperature T2 over here. So after that, what we can actually write?
So B and C will be in parallel.
Yeah, very good. So B and C will be actually parallel. So LB by KB into A by
A
2.
by 2.
Yeah, very good. So A by 2 is actually going to be there. So parallelly, we can actually give LC by KC into A by 2. Okay. Yeah. Now, basically, after this, it is actually going to be over here, which is actually T3. And again, we are having our fourth wall, which is LD by KD into A. And then for we can actually have the temperature. Okay. Yeah. So, as an electric analogy, what we can actually write is here Q is equal to QB plus QC. So whatever the heat flux which is actually coming, it is actually going to be divided across these two parallel, and then it is actually going out. Okay, so that is actually what we can actually get from here. Okay, yeah. So therefore, you can actually write which is actually equal to say T2 minus T3 divided by LB by KB into A by 2 plus LC by K. No, 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 okay, yeah, which is equal to, or which is plus T2 minus T3 divided by uh, LC by KC into A by 2. Okay. So now what we can actually do, we can actually take this T2 minus T3 is actually common. Okay. So then what we can actually write 1 by, what is this? This is actually the R resistance for B, right? R resistance for or thermal resistance for B section plus 1 by thermal resistance for the part C. Okay. So yeah, so therefore we can actually write as, so therefore Q is equal to, so this so in the in this yeah, in this middle section, the effective resistance comes at 1 by RB plus 1 by RC. Okay, so this is actually okay for us because from electric analogy also, from electric analogy, that also we can actually write as 1 by R parallel is equal to 1 by RB plus 1 by RC. Okay, so that's what we are actually writing for parallel resistance also. So that's what we are actually getting from his thermal analysis. Also, we are actually going to get. Okay. So therefore, if these things are actually comes in like this, then you can actually simply consider these things are actually as a parallel resistance, and then you can actually do the calculation. Okay. Yeah. Yeah. So this one we can actually write it as R total. Okay, R total. Therefore, we can actually write as LA by KA into A. Okay, plus, okay, R parallel. Some parallel resistance is actually going to be there, divided by LD by KD into A. Okay, so that is actually equal to LA by KA into A plus 1 by, yeah, so 1 by K KB into A by 2 divided by LC, okay, plus KC into A by 2 LB over here and LC over here, plus LD by KD into A. Okay, so this is actually 1 by 1 parallel, 1 by RC. So this is actually 1 by RB, and this is actually 1 by RC. This is actually 1 by RB, and this is actually 1 by RC. Okay. Yeah. So this is how we are actually writing this. This is actually equal to 1 by UA. Okay. This is equal to 1 by UA. Also, this is equal to, we can actually write T1 minus T4 divided by Q. Okay. So in different ways we can actually write. So that's how we are actually writing some series resistance, parallel resistance, and all those things. Okay. Yeah. So it will be more clear when we are actually doing one tutorial based on this. Okay. Yeah. Suppose if you are having this height as h by 4 and 3h by 4 and all, then basically you have to change it in the areas whatever we are actually assigning together with this particular section. Okay, so yeah, so that's how different problems can actually comes into the picture and all when we are actually changing these areas. So that also you can actually do. Okay. So anyway, mind that it is actually basically a 2D conduction only. Whenever there is actually going to be a slab, so at least in these particular sections near to the junctions, it is actually going to be 2D. Okay. But in this particular case, we are actually assuming this to be a 1D conduction. So therefore, we can actually use this electric analogy. Okay.
Sir, for B and C, it is not like 1 upon KB and sir, in last equation only.
Yeah.
Sir, like you have
No, this
written
is
1 by
actually this is
RB plus
actually
RC, no, sir. Hmm.
so this is actually 1 by parallel R parallel. Okay. So what we are actually writing is 1 by RB, right? So that 1 by RB we are actually writing here.
That is what I'm saying, sir. 1 by RB plus 1 by RC, but you have written 1 upon RB plus RC. That is different thing.
Oh, okay. No. 1 by R parallel. Okay, 1 by R parallel. So 1 by R parallel is 1 by RB plus 1 by RC. So 1 divided by 1 by RB plus 1 by RC. So that's what we have written, right?
Achha.
Is that clear? 1 by 1 plus RB plus 1 by RC. So 1 by can actually write as 1 by RB plus 1 by RC, right? Is equal to LA by KA into A plus what is actually 1 by RB? It is equal to KB by KB A by 2 divided by LB plus KC A by 2 by LC plus LD by KD into A. Is that clear now?
Yes, sir.
Yeah. Yeah, I know it is actually a bit confusing, like, but this is all arithmetic and all. So, but when you are actually doing, then you will actually get the hang of this. Okay. Yeah. So we have actually till now, we are actually are happy about everything till now. Okay. So we are having, yeah, we actually saw the complications, we actually increase the complications, right? So first we were actually seeing a single slab, then a composite wall we are actually seeing, and inside the composite wall itself, we actually started to see this. Uh, yeah, we actually started to see some kind of parallel series and all those things. Okay. Yeah. So now there is actually, yeah, but in all of these cases, what we are actually saying is at the junctions, okay, at the junctions, say material A and B, okay. So in the composite wall, if we can actually take between the materials A and B, there is actually same temperature. That means, so the surface of material A on this side, okay, on this side, it will be having same temperature as that of surface on the material B. Okay. So that means, what does that actually mean? That means there is the conductivity at that location is actually very efficient, and so the contact between these two materials are actually going to be very good. Okay, so then only you can actually have the same temperature. Okay. So the contact between these two are actually going to be very good. So therefore, the, yeah. So if you actually see the composite wall. So A and B. If you actually see this one, if you actually see this one, so here we are actually saying, okay, here we are actually saying the contact is actually going to be very good. Okay, contact is actually going to be very good. So therefore, this is actually the surface of A, and this is actually the surface of B. There is actually no distinction between these two. It is actually continuous, and therefore the temperature is actually going to be same. So that's what we were actually talking about. Okay, so this is actually the ideal condition. This is actually the ideal condition. Okay, so but in a practical condition, what happens is that, but in a practical condition, okay, practical condition, if you are having two materials A and B, okay, if you are actually zoom into this, what you can actually find is, okay, obviously the surfaces, they are actually not going to be smooth as it is. Okay, it is actually the material A, and this is actually the material B. So the, you can actually see that there is actually going to be some roughness associated with the surfaces A as well as surface B. Okay. So therefore, in between these two materials, what happens is that we are actually going to have the, there is actually going to be a gap between these two materials. Okay. So if you are actually having a gap, so what is actually the material that actually comes into picture? That is
Air.
actually going to be air. Very good. So therefore, we can actually see that the air is actually comes in between two surfaces. So therefore, it is actually kind of another material that actually comes into the picture. So if there is actually going to be another material and it is having some conductivity and all those things, so we can actually see that the temperature on the surface A, if we are actually giving it as T2, then obviously the temperature on the surface B, it should be actually T3. Okay, so therefore we have to write as T1, okay, T1, T2 and T3, and over here it will be actually T4. Okay, so that is actually the, there is actually going to be some resistance. It is kind of a resistance only, right? Okay, and that resistance is actually due to the contact of these two surfaces. Okay, so therefore we are actually calling this resistance as contact resistance. Okay, the contact resistance. Okay. So this is actually another important topic, okay, which is actually the contact resistance. Okay. We can actually write as in practical conditions. Okay, in practical condition, in practical condition, due to roughness, due to roughness of walls, roughness of walls, the contact is not perfect. The contact is not perfect. Okay, so not perfect. Okay, and and a gap between these two, and the gap is filled with surrounding fluid. Filled with, if it is actually dipped in water, then the gap is actually being filled with water. Okay? The surrounding fluid, okay, surrounding fluid, and what is actually the result? Which actually causes a temperature drop. Causes a temperature drop. Temperature drop. Okay, temperature drop. So the thermal resistance, kind of a thermal resistance, is actually acting on this. A thermal resistance is actually kind of acting at the contact, and it is actually known as the contact resistance. Okay, so a thermal resistance is acting. Resistance is acting at its contact, acting at its contact. Okay, and is termed as contact resistance. Okay, contact resistance. It is actually given by the term RT, C. R this is actually the thermal resistance due to contact, RT, C. Okay, so we can actually, if we are actually having a slab like this, okay, we are having a slab like this. So basically at the junction, we are actually going to have this kind of contact. Material A, material B, we are having temperature T1, here temperature T2, T3 and T4. Okay, so how we can actually write this? So here, due to conduction over here, we are having T1 and till T2, and due to contact again, we are having a resistance. Okay, so here it is actually going to be La by Ka into A. So here we are having our resistance, contact resistance. After that, it is actually going to be T3, and due to conduction in the material B, which is Lb by Kb into A, this is actually La, and this is actually LB, right? Yeah, and then we are actually going to have the temperature T4. Okay. Therefore, we can actually see that the contact resistance can be actually considered as resistance in series. Okay, so RTC can be actually considered as resistance in series. Resistance in series. Okay. Yeah. So actually, RTC, this contact resistance, it is actually very difficult to calculate it by some other basic principles or something. Okay. So it actually depends upon the roughness, okay, and it actually depends upon the gap between these two. And again, for different materials, we can actually see that there is actually a minimum roughness that is actually practically possible for different materials and all. So the combination of the material also influences this contact resistance and all. Okay. So therefore, this RTC can be accurately measured using experimental studies. Okay. So usually, experimentally studied values are what we are actually going to be using in most of the cases. Okay. Yeah. So yeah. So that's what. Yeah. But I haven't given the values. But in the next class, I will actually give the usual values that we can. The values that is actually from experimentally measured values for combination of different materials, etc. It is actually available. So those things I will actually give in the next class. Okay. So, but it is actually a good property or good effect or adverse effect. It's actually something we don't desire. Right? We actually always desire there is actually going to be perfect contact. Okay. So, but here the some temperature drop is actually going to be there and all due to some resistance and all. So this is actually something we actually don't like. Okay. So therefore, what we are actually going to do is here our issue is that in the gap whatever we are having is actually air, and we know that the conductivity of air is actually going to be somewhere around 0.029 26. Okay. Obviously, the convection etc. will not be actually happening over here because the gap is actually very less, and there is actually no option for the air to have a bulk movement of the air. So here the dominant conduction or dominant heat transfer process is actually going to be the conductivity only, even though we are having air in between. So therefore, what we are actually going to do is, so in order to reduce this resistance, what we have to do is, obviously we can actually try smoothening the surface, but there is always going to be a limit for smoothening the surface. Okay? So other thing what we can actually do is, we can actually remove the air in between and we can actually put some other material. Okay. So before tightening or before we are actually assembling this material, so we can actually put some grease in between, thermal grease with high conductivity and all. If we are actually going to put in between, so into the gaps, instead of air, we are actually going to have the grease. Okay? Or any soft material also, material that can be actually deformed very easily, metals like lead or something. If we can actually put in between these two, into the gaps, whatever is actually going is actually the soft material or soft metals. Obviously, there also the conductivity is actually going to be higher than that of the air. So in those ways, we can actually reduce the thermal contact resistance, but we cannot actually fully eliminate it. Okay. So therefore, yeah, these are actually some methods in which we can actually use to uh, reduce this thermal resistance. Okay. So thermal grease or soft metals. Soft metals are thin foils. Okay, soft metals are thin foils. Can be actually can be fixed between the contacting material. Contacting material to reduce RTC, thermal contact. Okay, so contact is, we know, L by Ka. Yeah, so if you are actually increasing the K by almost 10 times, if you are, or 10 or 20 times, if you are actually using an air, the conductivity is somewhere around 0.06. Thermal grease, it might be having a conductivity of say order of 1. So in that case, we are actually reducing it by 100 times. If you are actually using some material, it will be having a thermal conductivity of say 10 or 20. Okay, so likewise, we can actually reduce the thermal conductivity to a very large value, to very great extent. Okay, so that's how we are actually using this thermal grease of soft materials for that. Okay, yeah, yeah. So yeah, that's what we can actually see from 1D steady state condition without heat generation. Okay. We said that we can actually analyze this thing with the analogy of a thermal resistance. So it is actually very easy for us for the calculation of heat flux. Yeah, so from the next class, we will be actually seeing of 1D heat conduction with the heat generation. So once the heat generation comes into picture, then the electric analogy actually falls. Obviously, we can actually consider as a battery or something again fitted to the system, so which is actually going to be acted like a source of current and all. But again, that is actually going to be very complex. Okay? So therefore, what we are actually saying is this thermal analogy, we are mainly going to be used for a 1D conduction without heat generation. Okay? So in the next class, we will be actually seeing the 1D conduction with heat generation. The basic conditions like we will actually see how we can actually find this temperature profile with this heat generation, etc. How it is actually comes into picture. So that we will actually see in the next class. Okay. Yeah. So any doubts still here? Okay.
No, sir.
Yeah. Okay. So if no further doubts, we can actually stop the class here. Okay. So see that I have actually taken only 1 hour for today's class. Yeah, maybe this week we can actually take 1 hour for all. So yeah, and the Thursday we'll be having one Thursday or Friday. we can actually have one tutorial. I will actually send you the questions by today evening. So you can actually go through the questions by the time we actually take the tutorial. Okay. Yeah. Okay. Then have a nice day to all.
Thank you.
Thank you, sir.
Thank you, sir.